Shh. Okay, this is your favorite rule of the day. Today, you are going to learn the calculus of exponential functions. So we want to know the derivative of e to the x. E to the x is an exponential function, and here's what's beautiful about e to the x. The derivative of e to the x, Gavin? E to the x. E to the x is so wonderful because the derivative of it is itself. The derivative of it is itself. Nope. It's not. It's not. It's great. Sure. Gavin is very inquisitive about calculus. There's all sorts of things he's checked out. So I can't do the proof for you because it's actually it take me a little while to look back over it. It's kind of a tricky proof. But what I can do is show you this. I'm going to graph e to the x here, and I'm going to zoom 6, and you're going to see that exponential function, right? So watch this. I'm going to check the value. So I'm going to check a value. Give me number 1 through 10.
2.
Okay, so I'll check the value of the function at 7, and we get 1096.6. Can you remember that? Can you remember 1096.6? So I'm going to check the derivative now at 7. So I'm going to plug in 7, and I get 1096.6. You check the derivative, and it's always the same thing as the y value. Every time. Yeah, that's the beauty of the exponential function. Now, suppose that the base is not e, then the derivative of something where the base is not e, suppose it's b to the x, is b to the x times the natural log of b. Now, I do have a couple examples on your worksheet like that, but primarily that will not be used, primarily just be e to the x. So we'll go over an example here in a second, okay? So we look at letter A. I want to find this derivative. Does anybody have an idea of how I would find this derivative? Thank you, product rule. We call this f and we call that g. So f prime of x is equal to?
3x squared.
Good. Plus times x a third. Now, I would accept that on the test. Generally, you won't see it written like that on the AP exam. Generally, they'll take out the common factor. What's the common factor? X squared times e to the x. So if you take out that common factor, what are you left with? And that's often how you'll see that derivative expressed. And that's it. So we already know the product rule. We already know the quotient rule. We already know the chain rule. So all we're doing now is just teaching that the derivative of e to the x is e to the x. Anybody, what rule I use here? Nice idea, but I am going to use the chain. And what do you think is the inside? 4x squared. So then the outside is e to the u. So this is e to the u and 4x squared. See that? What's the derivative of e to the u? E to the u. Derivative of 4x squared? 8x. And so you get the derivative of the function is 8x e to the 4x squared. So you've seen it used with the product rule. You've seen it in this situation where it's the chain rule. We all good? Not too bad? Okay, I'll wait. It's okay. Thoughts on the rule that we use here? Quotient rule. F sits in the top, G sits in the bottom. Derivative of the top.
E to the X.
E to the x times 2 minus x. Minus the derivative of the bottom, which is negative 1, so it'll be plus e to the x. All over. Good. You won't see the answer written like that. You will see, well, there's a couple different ways you can do this. Yeah, you could factor out an e to the x if you want. Well, let me show you this piece. So suppose you distributed the e to the x. You would get 2e to the x minus x e to the x plus e to the x, all over 2 minus x quantity squared. What can you combine together? 2e to the x and e to the x make? Good. So f prime of x is 3e to the x minus x e to the x. Sorry. It's okay. It's unfortunate the class is required for graduation. So then, on this situation, then you could, if you want to, factor out the e to the x, get 3 minus x over 2 minus x quantity squared. So either one of these would be acceptable. But I want it either like that or like that. Well, you wouldn't have had, if you would have factored it out, you would have come up with this. Nope. Up to you. Okay, just 3 examples left. Notice I have a base of 4, so that's going to change this a little bit. We're going to have the chain rule. What's the inside? Tangent of x. And what's the outside? 4 to the u. What's the derivative of tangent? Positive secant squared. Very good. It's only the cos that have derivatives that are negatives. Okay. What's the derivative of 4 to the u? 4 to the u times the natural log of 4. All right, let's look back at the rule. The derivative of e to the x is e to the x. But if it's a different base, say b to the x, then the derivative is b to the x times the natural log of whatever the base is. So because it's a different base, namely the base of 4, you have to attach the natural log of 4 there. Okay. So now we just multiply these together. What do I plug in for u? 4 times tangent of x times the natural log of 4 times secant squared. And that's my derivative. What's that? So Marissa does ask a good question. I'll entertain this for just a second, then we'll move on to the rest of the piece. But what is a real application for this? So I'll give you an example here. So what happens if you get a clogged artery? Yeah, the blood stops, you have a heart attack, right? So what they do in the world of medicine is they put in what they call a bypass, right? And the bypass that is used, you know, what they basically do is they notch here and they notch there, and they, whoop, gotta go all the way over, huh? That bypass ain't working, is it? Yep. Yeah, we flatline there. See that? And so you get around. You're like, well, how is there math there? Well, the deal is that the this branch has to go on at an angle. Okay. And in order to minimize the viscosity of the blood flow, okay, so meaning that you want less friction with the blood flow, the question is, what angle do you put that in? Now, a surgeon that's not worth their salt, or not, what's the phrase? What's the phrase? I don't know. A surgeon that's not up to par is just going to put a branch in there however they want. But your excellent surgeon is going to say, we're going to find that angle that's going to minimize the viscosity of the blood flow. Now, where do I come up with that? My first calculus teacher, he worked at the Mayo Clinic. They had to have a math major on hand in the clinic that didn't know anything about doctoring, but was just there to solve problems. And so he had the doctors come into him, and they said, hey, this branch is supposed to go in. We don't know how it's supposed to go in. They said, can you do the math for us? He's like, well, sure. And his calculus involved that without a doubt.
How do they transfer that though? 62-degree angle, tangent of whatever, and then how do you this artery that's
right. You could ask, you could go and talk to a surgeon and get an idea. But I will tell you this. I will tell you this, that all of it just depends on the size of this artery and the size of this artery. As soon as you know those, you just do the cosine inverse, I think, of that ratio, and it comes up with the angle. So the doctors don't actually know the calculus, but the mathematician come up with the formula and make use of it for them so they know what they're doing, which is a nice deal. So, okay, 2 more problems. 3 more. How do you want to set this one up?
Keep the U, and then there's on the inside 3 sine to the third times x.
Yeah, so the inside is 3 sine cubed of the root of x.
And then the product formula.
Not quite.
Not quite, obviously.
This is 3 sine of the root of x, and it's that thing cubed. So that's what this means. So that's what we want to see. So what's the derivative of e to the u? Well, that was easy, right? But now I need the derivative of that. What am I going to have to do for the derivative of that? The chain rule. Okay. How do you want to set this one up? 3u to the third. And what's on the inside? Sine of the root of x. What's the derivative of 3u to the third? How do I do the derivative of sine of the root of x? Chain rule. Yep. So we have the sine of u, and what goes on the inside? Square root of x. What's the derivative of the sine of u? What's the derivative of the square root of x? So this is something, folks, this is kind of a measure point. We've done it probably a dozen times now. You need to start to convince yourself that the derivative of the root of x is 1 over 2 roots of x. If you don't see that, you've got to get that figured out, otherwise you're behind, seriously, okay? So now I multiply these two together, and I have the cosine of the root of x over 2 roots of x. So this derivative goes right here. Now can I multiply these two together? Yeah, and that's going to go in this box, isn't it? So I will have 9 times the sine squared of what? Root of x times cosine of the root of x over 2 roots of x. And so now all we need to do is take this times that, right? So I'll write that 9 sine squared root of x times the cosine of the root of x over 2 roots of x times e to what? That's my derivative.
simple stuff.
I would say so. I mean, if we had f of x plus h minus f of x all over h, that's how we used to find the derivative. We plug that into there, and we've got no shot. Like, we have no chance. Like, it's not being solved. We did that in 3 minutes. Could be a lot worse. Okay. 2 left. Try this one on your own. Ready, set, go.
Oh my god.
Okay, 5, 4, 3, 2, 1. Did you set it up like this? Good. So the derivative of u to the 1/2 is what? Good. So I'm going to pause there, and now I'm going to look at 4 minus e to the 4x. Now I know that's confusing to some people. What's the derivative of 4? 0. And so we really just need the derivative of negative e to the 4x. So all we have to do is just set up negative e to the u, and then 4x is here. What's the derivative of 4x? 4. What's the derivative of negative e to the u? So if you multiply those, don't you just get negative 4e to the 4x?
Every time for like e, it's like that. Where's that drop? That's so cool.
So Kaylee has noticed something. Folks, so you know, it's part just what you want to do in mathematics is just recognize when you have certain how should we say patterns develop. But what Kaylee has recognized is, suppose you have e to the x to the 6th. She says you don't even need to set up the chain rule. You can just take the derivative of that, which is 6x to the 5th, and just drop it in front. That's all that happens every time. Look at what happened here. Okay, you had negative e to the 4x. What's the derivative of 4x? 4. So it just drops in front. So if I have e to the sine of x, what's the derivative of sine? So it's going to be cosine of x, e to the sine of x. Yep, that's all that happens. So let's multiply it. What's 1/2 times negative 4? Negative 2. So negative 2 e to the 4x in top, and in the bottom we are going to have the square root of 4 minus e to the 4x. So negative 4 times 1/2 is negative 2. Yep. Okay, our last problem. Flip it over.
Are you available after school?
I am. The next one, secant of e to the a pi x. So there are no numbers in this situation. Well, actually, there's pi is a number, right? It doesn't look like numbers, though. If you notice, it's f of x, so x is referred to as the variable, so a is just a constant. That's just a constant. It could be like the number 4 or 8 or 25, whatever. So, yep. Anybody want to guess how we set this up? Chain rule. Very good. Secant of u.
E a pi x.
Good. What's the derivative of secant of u? Secant of u times tangent of u. And then the derivative of e to the a pi x.
Chain rule.
You don't have to set up the chain rule, but we sure can. E to the u, a pi x. Derivative of e to the u is e to the u, and derivative of a pi x. A pi, right? Just the constant. So a pi e to the a pi x if I could, real quick, I think that we have a couple questions here. Suppose that that was 9x. What's the derivative of 9x? 9. So it's just whatever the constant is, and the constant is a times pi. Okay. So we're going to multiply these two things together. We have finally f prime of x is equal to a pi e to the a pi x times secant of what? E to the a pi x times tangent of e to the a pi x. Nope. Which part, Tim? All right. You guys can now start your derivatives of exponential functions. You guys are ready to go. You got about 15 minutes. Hi.